Okay, so we're just going over 3 vector word problems from last night, starting with number 23, which says, a force of 36 newtons pulls an object at an angle of 20 degrees north of due east. So north of due east is your René Descartes standard angle. North of due east, you can just call that 20 degrees and that 36 newtons. Have I read that correctly?
Yes.
Excellent. A second force pulls on the object with a force of 48 newtons at an angle of 42 degrees south of due west. South of due west. So due west would be this way, and 42 degrees would look something like that, and I should make that vector larger to represent 48 newtons. I'm probably never going to pull out a ruler on your test, but I should see some effort on your guys' parts to make your vectors proportional to the magnitudes they're talking about. So, find the magnitude and direction of the resultant force. All you gotta do is break these vectors down into their horizontal and vertical components and add them. The only real issue with this is keeping track of the positives and negatives. So we can do this a couple of different ways.
Well, as vectors is going to be different, but these are forces, so they act a little bit different.
Nope.
Am I wrong?
This
Nope,
is
they're
kind
just
of a
vectors.
weird question, but if
Yeah.
we wanted to, like, I understand it kind of like is a coordinate plane, but could we just draw this on a coordinate plane?
Yes.
Like, so it's like a compass in my mind?
Yes. We could do it that way. That'd be perfect. You could draw it on the coordinate plane. You could also move these around to get a I'll do that in a second, actually. First I'm going to do this algebraically, and then we'll double check graphically if it seems to make sense. So I'm going to call this force 1. I'm going to call this force 2. I think that's what the book does. So force 1 is going to be the vector 36 cosine 20 degrees, comma 36 sine 20 degrees. That's pretty much the only rational way to write that force. Force 2, we have 2 ways to write it, depending on your level of comfort with the unit circle.
Wait, aren't they negatives?
Yes, if we're going to use the 42 degrees, which would be a reference angle, then we have to remember to make both of them negative because this vector goes to the left and down the way we've drawn it. So that's 48 cosine 40, negative 48 cosine 42 degrees, negative 48 sine 42 degrees. Or we can change it from a reference angle to a standard angle.
Would you add them, or?
108, wait, in a moment we'll add the components. But 180 degrees plus 42 would get me 222 degrees.
Oh, so you always add? Oh yeah, you would always add.
Yeah, hold that thought a sec. We can use positive 48 cosine 222 degrees, positive 48 sine 222 degrees as well. Someone double check that I've got the standard angle correct there. So 180 plus 42, really 222?
I think you're all good.
I think so.
That's what I got.
Excellent, stick with the mental math. And now we add the 2 vectors together. So when we combine forces, we're just adding them. This doesn't need a dot product or a cross product for this one. And this is the point where someone would pull out their calculators and discover that, I'll write that up here, that F1 plus F2 added as vectors equals, who's got the numbers?
Negative.
2.62 and negative 15.79.
I got I got negative 1.84.
Let Mary Joey's down first. What's the first bet? 2.62 and what else?
15.79.
Positive 15?
No, negative 15.79, I'm sorry.
Okay. Noah, what did you get?
I got negative 1.84, comma negative 19.8.
Okay. Anyone else have any different votes?
Let me try to add those also.
Yeah. Show what are you getting? Well, actually, before anyone gives me a number from a calculator. Hold up.
I get what Noah gets.
Okay. Before anyone gives me something from a calculator, there's a quick way to double check who might be in the right ballpark.
Oh wait, never mind. No, I was wrong.
Okay?
Problem solved.
Well, let's double check this graphically anyway. Does this look like it's about a 20-degree angle?
Yeah.
Okay? Going tip to tail, see if that's 36, and I want to go, if that's 20, that's 20. 42 is pretty close to 45. Go straight down there for a little bit longer.
That's really annoying.
That's 36 and that's 48. Does it look like from here to here? Now remember, to find the resultant, we would go from this tail to this tip. Okay, it's like, what's the shortcut? If this is the distance, what's the displacement? And does this resultant vector look like you could get it by going a little bit to the left and then a little bit more down?
Yeah.
That looks, so negative 1.84, negative 19.8 looks reasonable to me. But I mean, I didn't pull out a ruler and check the scale, so.
Well, it's annoying to, or well, not annoying, but I realized the important thing with vectors is that you gotta remember you're trying to find the displacement where you end up.
Yeah, it's a good way to look at it. The end, when you're done adding the vectors, the result is like your displacement, and the vectors are like your distance. So that's a good way to think of the difference between them. So that one I think was pretty straightforward, though the numbers were ugly. This could have been a good place to mess up.
And I just added those, or at least the x, and it's 1.84.
Okay, negative I hope.
For some
Yes.
reason, I did 45. Like,
For the angle or for the length?
no, for the length. I don't even know where I
That would
got
give you
that.
slightly different numbers.
Yeah.
And I also got
Averaging these two?
negative 19.8.
Good, 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 good. Okay, so that's number 23. Any questions before I erase it?
Didn't we have
Once.
to find the angle?
Let me read the question. Find the magnitude and direction of the resultant force. Thank you. Okay, so for the direction, theta is going to be the inverse tangent of the y component of the resultant divided by the x component of the resultant. My v sub y looks like a square root sign. Actually, that's because I was going for an r sub y, the resultant, and the y component.
You get the angle to be 84 or 85.
84.7.
Well, remember what I told you about the tangent now?
But you also have to add, like, because it's in quadrant 3, you have to
Very
add
good.
180, so then it comes out to 265.
265 degrees. Okay, I'm trusting you on that one. Remember your calculator, if you put in positive, you only get the reference angle in quadrant 1. If you put in negative, you only get the negative angle in quadrant 4. Your calculator will never give you answers from quadrants 2 and 3.
Can't like we say that it's like 85, but it's south of east?
In this question, yeah, that would be consistent with how they phrased it. So 85 south, is it south of east or south of west?
Never eat soggy wheat.
Really? But isn't the result, but the result's in quadrant 3.
Okay, so I mean south
South
of
of
west.
west,
Okay,
yeah.
so couldn't we like just state it like that?
85 degrees south of west would be fine.
Okay.
That'd be fine, or 265. You gotta look at the directions. In this case, I would accept either, though 85 degrees south of west is probably better to be consistent with how the books gave you the first two angles. But I'd accept 265. Obviously, if it says, give me this that direction as a standard angle, that's what I'm gonna want. Thank you, Noah, for remembering that we hadn't finished the problem. Okay, that's 23. Shall I get rid of this now? Okay. And 24.
You should probably do. You should have probably taken a picture of her. So.
Well, we got on video, so
Oh, I guess that's true.
hopefully she can freeze frame. 24. Three forces in a plane act on an object. The forces are 70 pounds, 115 pounds, and 135 pounds. The 70-pound force is exerted along the positive x-axis. Michelle, I'm sure you drew a very neat.
I tried to draw it, but I don't think I understood.
Alright, I'm sure you drew a very neat XY coordinate.
This
pointing
one
for
was challenging.
Alright. The 115-pound force is applied below the x-axis at a 120-degree angle with the 70-pound force. So what they're telling you is that the 115-pound angle makes that, goes like that. Okay? And then the 135-pound angle, I'm losing this up. The angle between the 115-pound and 135-pound forces is 75 degrees, and between the 135 and 70-pound forces is 165. Okay, 2 bits of information there. If all they tell you is that the angle between the 115 and the 135-pound force is 75 degrees,
Can't you just add 75?
well, you don't know for sure whether that 75 went back this way or continued
That way.
clockwise that way. The hint they give you is the angle between the 135-pound and the 170-pound is 165 degrees. So if it went back this way, do you think that's a 165-degree angle between those two? No. So,
And I think 75, 165, and 120 all add up to 360.
very good, sir. Excellent. So that's 75, which I've actually drawn as slightly larger than 90, so please forgive my lack of scale. And this would be the 165. So those are the 3 forces, and they're all acting on an object. Ms. Good would tell me that was wrong. If I use identical arcs for all 3, I'm saying they're congruent, and I don't want to say that. So I should distinguish them somehow. I want to be grammatically correct with my math symbols.
I don't think the math whatever is going to come in front of you.
But I want to hold, but you know, there's a sort of grammar to math that we want to follow. Make a diagram showing the forces.
Interesting.
Check, check. Okay. B, are the vectors in equilibrium? If not, find the magnitude and direction of the resultant force.
I tried to look up what equilibrium meant, but I just got like to this work page in our book and it had no definition, and I was like,
Equilibrium means,
They all add up to
That
0.
is like
in this case it means they all add up to 0 mathematically. It would mean they all add up to 0. In general, equilibrium is sort of a moving equivalent to balance.
okay, because I knew it had to do with something with like equaling
Right.
and like,
Equilibrium is like dynamic balance. You know, so things are truly balanced if they're still. You know, if you and I are tugging on a tightrope, if you and I are tugging on a rope, just having a tug of war, and no one's moving, that's not really a still thing. There's a lot of forces going on. So that would be more equilibrium than balance.
alright, but then it would be like if those all add up to 360, 360 and 0 lie on the same point.
Yeah, but they're different magnitudes.
Okay.
And they're not evenly spaced. That's a good point. There's a lot of assumptions that can seem intuitive that you wouldn't necessarily be. For example, here, Michelle, if I'm pulling with one force this way, and you and Daryl are pulling with the exact same magnitude,
You think
these
it takes
ways.
2 of us to be?
well, if these forces really are equal, you guys are gonna totally drag me across the floor. Because the fact that they're not, these angles will all add up to 360 as well, but the fact that they're not evenly spaced means I'm getting yanked this way by twice as much force as I'm pulling. So I'm gonna go flying. If we were evenly spaced, if this were, all of these vectors were 120 degrees apart and the same magnitude, then you have equilibrium. Or,
Well,
And
that
we'd
also
be going nowhere.
comes out to 60.
It's like if
Wait.
we just like
no,
pull each
120,
other.
120, 120, 360.
And
You're thinking triangles.
and y'all go no.
Yeah, but if you move the vectors around
Is that right?
to that, it would come back to the horn.
Okay, hang on, Noah. Hold that thought. Now, in order for this to be equilibrium, I would have to pull not quite twice as hard, but a lot harder than both of you for that to be equilibrium
Yeah,
because
yeah.
of the way they're faced.
No, if you did it like that, Mr. But if you moved the vectors around to a triangle, then it would be all 60.
Yeah,
And-
but we're not going to do that.
Yeah.
Okay.
But an equilateral triangle is all 60.
Yes. Okay. So, in this particular case, you add up the vectors, see if you get 0. First vector is pretty simple to put in component form. That vector is 70, 0. That's this first one. Okay? It's just going along the x-axis, it only has a horizontal component. The next vector It's 115 pounds, not degrees. No, that's the 135 pound one. I totally mislabeled that. This is the 135 pound force. So that's going to be 135 cosine 165 degrees, comma, 135 sine 165 degrees. By putting in 165, it'll automatically make the x component negative, and sine 165 will still be positive. This one, the 115 pound one. Fastest thing to do with the information we're given, if you want a standard angle, since this one's going along the x-axis, add 165 to 75. And you'll get 115 cosine.
Wait,
240.
240.
165 plus 75?
Yep.
Yeah, that's 240.
115 sine 240. That way I don't have to spend a lot of time figuring out, okay, it's 15 more degrees to 180, so then it's 60 more degrees from there to get to that angle. I can just plug it in. Add these three numbers to get my x component. Add these three numbers to get my vertical component. And the sum, physics kids, my sigma symbol, remember that? Of all the forces is going to be
Negative 117. 118, I suppose.
I should have two. So who's got, let's double check that. Which component, which one was that component, no?
That was x.
X, what'd you get?
Do you want a decimal point? Or?
Yeah.
Negative 117.9.
Yeah, I got that too.
Okay.
And then negative 64.7.
Negative 64 point, which?
7.
7. Okay. What's the magnitude and direction of this resultant, of this answer? How do I find the magnitude, how much of a pull this is on this object? How do I find the magnitude of any vector given the components?
You do
tangent.
you met the magnitude.
The
Yeah.
square root of
Like
the
of 100 of negative
Yeah.
117.9
x
plus.
squared plus the y squared.
Yeah.
Pythagorean theorem, basically, is going to be the magnitude of this resultant vector. Anyone get that yet?
Yeah, that was 2. Oh wait. Oh crap! No, I didn't.
The book had, I can tell you what the book got.
Oh no, wait! It was 134 pounds.
Okay, the book got 134.5.
Oh,
I'm not sure where they rounded, but very close.
let me see.
So 134.5 pounds. And what direction is it going in?
209 degrees. So.
Sounds,
Well, wouldn't you do theta equals the? Yeah.
yes I would.
Okay, I would just do.
And what do you get with that if you use both positive x and positive y? Same thing as if you use both
Yeah,
negative,
they're-
actually.
The book is right. It's 134.5. For
Excellent. And what do I get for this angle?
Let me do it before the book does it.
The book gives the answer in a funny way. Oh, I see how the book does it. Okay.
With 28.
28.8.
28.8 degrees. Now, with that, okay, what does that 28.8 degrees mean? Which way do you think this is actually going?
It's going like.
In the third
But
quadrant.
because there are two negatives, then it's in the third quadrant.
Yep, with these two components, you know, based on these two
Yeah.
components, you know it's in the third
And
quadrant.
then you just add 180, so then
So the actual direction,
208.8
Southwest.
degrees.
Or can you just say southwest?
can't just say southwest, you can say 28.8 degrees south of west. But remember, most of our textbooks, when they see southwest, they assume you mean exactly 45 degrees into quadrant 3.
South. So then what would I say?
28 degrees south, 28.8 degrees south of west.
28.8 degrees south of west.
That's how you would say that.
Or do.
But I'm a big fan of standard angles. Actually, I like those. All right, any questions on this one? Fairly straightforward, a little more straightforward than the examples I gave yesterday. Oh, here we get to a more fun one. This one's much more fun.
No, I would have to say 24 is confusing, like knowing where you have to put the third angle.
Yeah. It's probably a little close to the microphone. Let me get you something
Sorry.
quieter to test.
Sorry.
Yeah, it's alright.
Everything
Quiet
that's fun to
clicker. Give
fidget
you the
with.
tactile without the noise.
Okay,
may I?
Everything that's fun to fidget with makes noise.
I know. It's horrible. Can I go ahead and get rid of this board?
Yes.
Okay. And now let's take a look at 29 with our unicyclist. These are ones where I often make a silly mistake myself setting it up, so double check me on this. Alright, we got our unicyclist. Unicyclist is performing on a tightrope at a circus. The total weight of the performer and her unicycle is 155 pounds. How much tension is being exerted on each part of the cable? Okay, so, a little drawing here. Looks like she's most of the way across. That part really doesn't matter. The length of the rope, the length of whatever's carrying the force or conducting the force, really doesn't matter. It's the amount of the force. So here's my unicyclist. It's as good a stick drawing of a unicyclist as you're going to get.
They have like a weird body. They have a snake body.
Very impressed, actually.
If you can tell what it is, I'm thrilled, but thank you, Michelle. So that's 5.5 degrees over here, and this is
6.2.
6.2 degrees. Okay, now she and the unicycle combined exert a force on the rope of 155 pounds. So the forces can only go along the ropes. They can only go in those directions. And if the resultant vector is 155 pounds straight down, the reason why she's not falling to her doom is because the result of what the rope is doing, the rope is creating a 155-pound vector going straight up. If the rope weren't creating that vector, she would be falling. If the rope were pushing up with more than 155 pounds of force, she would be rising off of the rope, which would be bad. Now we have to figure out two vectors that go in these directions and add up to this positive vector that's keeping her from falling. And they have to go in the directions of the rope. This would be a little bit difficult to draw to scale. Okay? So, and I'll show you why in a sec. I'm trying to think of a better way to phrase it than I did yesterday. But think about what happens graphically when you add vectors.
Could you add the angles up and do that?
No, adding the angles up won't help. But I've got an idea that I think is a better sort of strategy. Remember what I just said a minute ago about how you can think of the resultant vector as displacement if you think of the vectors that add up to it as distance. Okay? So imagine this for a minute. You start here, and you have to wind up here, and you're only allowed to travel at a 6.2 degree angle or a 5.5 degree angle. And the 6.2 degree angle, has to go in that direction. So this will not be to scale. I'll try to draw to scale, and that'll be kind of funny. So here's my horizontal. If I go up at a 6.2 degree angle, okay, I have to keep going out here until I get to the point where if I turned around and went up at a 5.5 degree angle, following this path, this distance, would create this displacement. Okay? So I have to start at the tail of my resultant vector, and I can only follow the angles made by the ropes, and I have to get to here. If you think about that, there's only two ways to accomplish that. One would be to go up at 6.2 degrees in this direction, and at some point stop, and then go up at 5.5 degrees in this direction. The other way to accomplish that would be to go in this direction at 5.5 degrees,
Are you sure it's...
and at some point turn around and go back up at 6.2 degrees. Am I sure? And the arrows have got to follow the path of your journey, your alternative journey. No, please double check me on any details. Am I sure about
Oh,
that?
I thought it was 115 pounds.
Okay, no, I think it's 155.
No, it's 150.
Okay. So now the question is, what's the magnitude of each of these vectors? There's a couple ways to do that.
It's not gonna be split in half.
No, because of the different angles and there'll be different
This
magnitudes.
is interesting.
Be close. There's a couple ways I can do this. I can break them down by components, but yet, unlike the one, the picture frame one had a better hint, because the picture frame one we could cut in half because it was right in the middle. Okay, and the sine one didn't add up this way. But here's where we're going to remember some geometry and some stuff we
Could
did
you
before.
make it like a whole, whatchamacallit,
I have to know what a whatchamacallit is, no?
what's that diamond shaped object?
I'll make a parallelogram?
Yeah.
Yeah, I don't think that'll speed things up, but we could do that.
Well, isn't there
Some
some
people like that.
I forget it, but isn't there some formula to find that distance, the diameter or whatever?
Knowing one diagonal
Yeah.
of it, probably. Yes. I don't think it's faster than what I'm going to show you right now. You need one that's show you right now. Okay. If I draw a horizontal here through this vertex of this triangle, I've got a horizontal down here. These horizontals should be parallel, right?
Yeah.
And if these two horizontals are parallel, and there's a 6.2 degree angle down here, what do you think that angle has to be?
6.2.
6.2. They're alternate interior angles of a transversal connecting two parallel lines.
The geometry is coming back.
I hope so. Which means this total angle here has to be what, 11.7?
11.7.
That's what
And then those two have to be equivalent, like down there. So if you
Well,
do-
even slightly simpler than that, if this is perfectly vertical and this is horizontal, what do these two angles have to add up to?
90.
90. What's 90 minus 6.2?
83.8.
83.8. If that's 83.8, well, there's a couple of ways we can do this. This one up here is also an alternate interior angle to the 5.5 degree one, and these two have to add up to 90. We can also say 83.8, 11.7 plus blank equals 180, but I think this will be a little faster, so this should be 84.5.
Yeah.
Okay. If you know one side, and you know the angle opposite in the other two angles,
Oh, this is
law of sines or law of cosines?
Um,
Law of sines, I would say. So I would say the sine of 6.2 degrees over 155. No, that's messed this up. It's 11.7. School me, Michelle. Tell me how to do this. Sine of 11.7 degrees over 155 equals, bless you, the sine of 84.5 degrees over the magnitude of one of my vectors equals the sine of 83.8 degrees over the magnitude of my other vector. And I can solve each of those ratios separately with a little bit of cross multiplication. A little bit of rearranging. Vector 1 multiplied by sine of 11.7.
Is 155 sine 84.5 divided by sine 11.7?
Somebody remembers the pattern from last time amazingly well. Yeah, it'll wind up being 155 times the sine of 84.5 divided by the sine of 11.7. This is a decimal close to 1, so this answer the numerator should be a little less than 155. This is a decimal not that far from 0, so then it's going to wind up getting a significant amount larger after that. So what do we actually get?
760.
That's even bigger. Okay, so 760 pounds along the vector. Let's see, 84.5 came from the 55.5. So that's this one. Because I got that from the 84.5 degree angle, which was the complement of the 5.5 degree angle. So that's how much tension is on the side where the angle's 5.5 degrees. Vector 2 is going to be 155.
Sine 83.8 divided by sine 11.7.
Wait, when was this? This is law of cosines or
Law of sines. Law of cosines was the a squared equals b squared plus c squared minus 2ab cosine c. So what are you getting here? 761. That's what the book has. So there's 760 pounds of tension in this part of the wire, and 761 pounds of tension in this other part of the wire. That's what makes, now these two vectors of 760 pounds this way and 761 pounds this way, it makes sense that they add up to 155 when you add them as vectors and take the directions into account. If you think of them as numbers, it makes far less sense. 761 plus 760 does not equal 155.
Yeah, that's why I was so shocked when I got the answers.
Oh wait, it's 760 though.
The book says 761. And there should be a very slight difference.
Oh, no. I think because this one with the 760, it was like 760 point like 6 for that, so that should go into 761, and that one should be 7.
60? Did I put them backwards?
Oh.
Well, wait a minute. Wait. No, I did not, and I'll tell you why I know I did not. Triangle inequality theorem. No, not the triangle inequality theorem, what I call the Goldilocks theorem.
Oh, the
What
bigger
side
angle has to correlate with the bigger side.
Yep, the bigger angle. So the if these are the right numbers, which the book has, although they sometimes I disagree with, but not so much this book so far. The larger vector has to be opposite the larger angle, and the smaller vector has to be opposite the smaller angle, and this angle is very slightly smaller. That's another way to double check your answers on a test.
Isn't that the 6 point?
It's saying
The
that
761 is the one that goes up at a 6.2 degree angle, and the 760 is the one that goes
So that
up
should
at
be
5.5.
761, not 762.
I don't have a 2 anywhere on here. That's not meant to be a 2. I was trying to distinguish the 1 from the L in pounds,
Oh, okay, so
and I was trying to make it, a fancier one.
now I understand
I
everything.
should just do pounds like that. Okay, so, but does that help a little to think of like, if you have a resultant and you're trying to figure out what vectors add up to it,
I get it.
think of that as the displacement, and you're looking for a distance that has to follow those paths.
Gosh.
And that might help you set these up a little bit better. But yeah, one way to double check your answers on a test real quick, would you expect two answers very close to each other, using the law of sines here, with this one slightly larger?
Yeah.
Yes, because those angles are close to each other. It fascinates me that, it always fascinates me how counterintuitive this gets with just, once you start applying pressure at angles, holding something up at these kind of angles, just, it's ridiculous how much tension can be in the wire.
Jeez.
In fact, like I said, this model does fall apart at one point, because if this angle goes to 0, the sine of 0 is 0, we'd be dividing by 0, but I don't think that creates an infinite amount of tension in the wire. That would be exciting.
I've seen it happen.
that's
So there's a paradox there. Homework tonight is review work, which is online, and I've put it up over here. I'll go ahead and put it on the video for Jen. And it sounds like more than it is. It's basically over Thanksgiving break I gave you one problem of every type we've done since the last test. Exactly one. So that's, works out to page 479, 41 to 53 every fourth, and page 545, 4 to 44 every fourth. So it's one dot product, it's one cross product, it is one normal form of a line, it's one distance between two parallel lines. It's one of everything we've done except for these word problems, actually. So that should, it's not as many as it looks like. It's a little bit more than one night's worth usually, except for those nights before test where I let you have time in class. But that should let me not have to review too much when I see you guys again in a week. Questions, comments, concerns, or compliments?
Nope. Happy Thanksgiving.
Happy Thanksgiving. Happy Thanksgiving, Jen.
Oh,
We are out.